In the previous section, we added FPGA I/O to a LabVIEW project and accessed FPGA I/O in an FPGA VI. By the end of this module, you will be able to describe different FPGA I/O data types. So in this slide, we have an overview of different I/O types that are available to you on FPGA. So here, we've got a digital line, and that's going to write and or read a Boolean value to and from a digital line. So it's going to be one line, and you're going to be able to send it a true or false to either set that line or read the value of that line. We also have a digital port. A digital port is a collection of digital lines. So if we take a look at that screenshot there, we have a DIO port control, which is a 8-bit unsigned number going into the DIO port 0 there on the IO node. That 8-bit unsigned integer is actually representing 8 separate digital lines. We also have analog I/O. So this is going to allow you to read or write data from an analog channel. So in our series, analog I/O is going to be represented by integer values, and we'll talk about this more later. And compact RIO will generally represent that using fixed point data types. There are also other I/O types for other specific modules. So there are motion compact RIO modules out there, and those will have their separate I/O type, and also CAN modules as well. So let's talk about digital I/O. So if you're wanting to set or read individual lines, then that's going to be using a Boolean data type. So each line can either go high or low, and that's going to be represented by a true or false Boolean value. A port is going to be a collection of lines. So it could be a collection of 8 lines or 16 lines. So with a port, you're going to indicate that with an integer data type. So if you're trying to do a port of 8 lines, for example, you would need to represent that with an 8-bit integer. Depending on your hardware, digital I/O can be either unidirectional or bidirectional. So for example, you might have a digital line with a particular module that only does digital output, or another one might only do digital input. Some hardware can do digital I/O on each line, so each line can either do input or output. So if your digital I/O line or port is bidirectional, and you want to change the direction of the line or the port from the FPGA VI, there's a method for that, and you would just select the set output enable method and determine it that way. So later on this lesson, we'll talk a little bit more about I/O method nodes. So here we have a slide talking about creating counters from digital I/O. So an FPGA does not have built-in counter hardware, so there's not going to be a counter line. So if you want to implement a counter, you would have to program that in FPGA. The minimum input pulse width detectable is going to depend on the loop period and also your hardware. As fast as that loop is running, that's how fast it's going to be able to detect a minimum input pulse. On some hardware, you can get improved performance by replacing the while loop with a time loop. So a time loop is going to be something called a single cycle time loop, and we'll talk about that in a later lesson. So let's take a look at this block diagram here. So what we see here is an implementation in FPGA for a counter, in particular a 16-bit rising edge counter. So let's focus on that top part for now. So on the top part, we're reading from the DIO 0 line, and essentially what we're looking for is take a look at that greater than function. We're looking for a point where the top input is going to be true and the bottom input is going to be false. And that's going to represent a rising edge. So if you think about it, a rising edge is when that digital line goes from a false value to a true value, which is the same thing as it going from a low voltage to a high voltage. So every time that greater than function detects a rising edge, it's going to go down to the bottom section of this code, and it's going to increment the count. So essentially, you'll see that in that U16 integer, we're keeping track of a 16-bit count. Notice also that the loop condition terminal has an input of false, so this loop is just going to run forever. Also, if you look on the left side, there is a Boolean for resetting, so if that Boolean goes true, then it's going to reset the count back to 0. Let's talk about analog I/O. So different devices are going to have different default data types for analog I/O. So for example, if you're using an R series device, the default data type is going to be a signed integer. So you're going to have a 16-bit or 32-bit signed integer depending on which device you're using. So for R series, that data is going to be raw. It's going to be calibrated, but it's going to be unscaled. So that 16-bit or 32-bit number, if you want to convert that into engineering units, you're going to have to go from that that number into a voltage, so you'll have to do some scaling. And we'll talk about that more later. If you're using a compact RIO module and you're doing analog I/O, generally you're going to get your data returned as fixed point data, and this data is going to be calibrated already. So we'll talk about fixed point a little bit later in some of the later lessons. If you need to do floating point operations or analysis, you can either do this on the FPGA or you can also do it on the host.